According to CDC, 1 in 4 US seniors experience a fall each year. The repercussions are severe, with many leading to severe injuries or even fatalities. Moreover, the median EMS arrival time of such incident can be 18 minutes or more, especially in rural areas. So our goal was to create an affordable, always-on AI assistant using just a webcam and a microphone to detect falls and distress calls in real time. Our mission was to develop a proof-of-concept system that continuously monitors for falls and distress calls without the need for expensive hardware. The system comprises two main components: a vision-based fault detector and an audio-based distress keywords recognizer. By fusing data from both modalities, we aim to accurately assess the urgency level of situation and trigger appropriate alerts. The vision module captures frames via webcam, processes them through media pipe blaze poles for pose estimation, and apply a heuristic that detects falls based on torso angle and head-hip distance. Simultaneously, the audio module captures sound through a microphone, segments it using voice activity detection, transcribes it via Google Speech-to-Text API, and scans for distress keywords. The decision logic then fuses both outputs to determine the urgency level, logging events for further analysis. We utilize publicly available datasets to train and evaluate our system. For the vision module, we use fall detection dataset comprising 13,000 labeled RGB image of falls and normal activities. For the audio module, we employed the speech emotion recognition for emergency calls dataset containing recordings from 18 speakers expressing various of emotions, including distress. These datasets provide a solid foundation for developing and testing our modules. The watching module processes each frame by resizing and converting into RGB format. Media pipe blaze poles then estimate 33 key points per person, providing detailed pose information. We apply a heuristic that calculates the torso angle relative to the floor and the vertical distance between the head and hips. If the torso is near horizontal and the head is close to the hips, the system flags it as a fall. This approach is computationally efficient, enabling real-time processing even on mid-tier CPUs. In addition to the pose-based heuristics, our motion module incorporates an advanced action recognition model using a 3D convolutional neural network. Specifically, we utilize PyTorch Video's slow R50 model, renowned for capturing temporal patterns efficiently from video sequences. This enables the system to accurately recognize complex actions such as falling or difficulty standing up. By integrating this advanced neural network, we significantly improve our detection capabilities, ensuring critical events like gradual falls or struggles are efficiently identified. In addition to detecting actions and postures, our system incorporates object detection using YOLO V5, a fast and accurately model widely adopted in real-time computer vision tasks. This module helps us to accomplish two crucial goals. First, it enables us to track potentially hazardous items in the environment, such as furniture, sharp corners, or objects on the floor that might pose risk for falls. Secondly, and more importantly, it allows us to locate the elderly person in the frame at all times. This spatial awareness can be cross-referenced with our pose and scene recognition module, enhancing our ability to assess the severity of a situation. For example, if a fall occurs near a sharp object or staircases, the system can immediately escalate the alert level. This integration of object tracking strengthens the contextual understanding of each incident and contributes to a smarter, more informed decision-making. Beyond pose and action detection, we're extending our watching module to include comprehensive scene understanding. Leveraging semantic segmentation using DeepLab V3, our system can identify different areas within the room, such as kitchens, bathrooms, or potentially hazardous zones like stairs. However, we encounter some challenges. the module occasionally misinterprets the windows with outside views and incorrectly flagging them as hazardous area, and has difficulty detecting precise edges. We are actively refining our segmentation algorithm to address those issues. In our 10-sample validation run, the fault detection module achieved 70% accuracy with perfect precision, meaning no false positive. However, the recall was also 70%, indicating some faults was missed, particularly slow sliding descents that doesn't meet our heuristic threshold. This result suggests that our system is conservative, prioritizing avoidance of false alarms, but there's room for improvement in capturing subtle fault events. And here are some positive results of recognizing a fault, and here is a false result, an active result. The listening module began with segmenting audio using energy-based voice activity detection. Each segment is then transcribed using Google's speech-to-text API. We apply a regex-based keyword search to transcripts, scanning for terms like help, emergency, and pen, or even ambulance. If any keywords are detected, the system flags the audio segment accordingly. The straightforward approach allows us to quick identification of potential distress calls. Our audio detection capabilities are being enhanced through several advanced methods currently in development. We're integrating robust speech-to-text technologies such as VEC 2.0, which significantly improve transcription accuracy under challenging acoustic conditions. Additionally, we are incorporating natural language understanding with models like BERT to better interpret spoken context. A key advancement is the context tracking using transformers, enabling the system to detect sequence of distress indicator over time. For instance, the system will interpret phrases like "I don't feel well," followed by "help me," or "I feel dizzy," combined with "I can get up" as high urgency situations, thereby facilitating more timely and appropriate responses. Our audio module faces significant challenges that are consistent with industrial benchmarks. As highlighted by recent research presented in InterSpeech 2023, automatic speech recognition, which is ASR system, regularly experience accuracy drop below 50% when dealing with emotional or noisy speech environments, and our test confirms the challenge. We achieve a high recall of 80%, meaning we successfully capture most distress calls when present. However, precision was only around 50%, indicating many false positives caused by background noises and emotional vocal distortions. For instance, screams, cries, or panic breathing often disrupts typical phony structures, leading standard ASR systems like Google speech-to-text to misinterpret or even hallucinate keywords. To enhance reliability, we implement a simple decision logic that fuse outputs from both modules. If either a fault or distress keywords is detected, our system raises a medium alert. If both are detected within a short time frame, it escalates to a high alert. This fusion approach helps reduce false positives and ensure that critical events are promptly identified. We evaluate our system using an 80-20 train validation split for the vision module and a leave on speaker out approach for the audio module. Metrics such as accuracy, precision, recall, and F1 score were calculated using sklearn, and the vision module process frames at approximately 8 frames per second on standard CPU, while the audio module operates in real time for short audio segments. The vision module demonstrates strong performance with 70% accuracy and a perfect precision. The high precision indicates the system effectively avoids false alarms, a crucial factor in maintaining users' trust, of course. However, the 70% recall suggests that some faults, particularly those with gradual movement, were not detected. Incorporating temporal context through sequence modeling could help address these limitations. The audio module achieved 80% recall, successfully identifying most distress calls. However, the precision was only 50%, indicating a significant number of false positives. This outcome underscores the challenge of accurately detecting distress keywords in noisy or emotionally charged speeches. Further improvements may involve integrating more advanced noise-robust speech recognition modules, maybe like Whisper Tiny or the one I just introduced. And here's a sample of what we are trying to train our model using the dataset. We're actually capturing the sound in these different videos to actually train our model. And next, our current system has several limitations. It processes a static frame without temporal context, assuming a single person in view, and relies on cloud-based speech recognitions, which raises privacy concerns for most people. So moving forward, we plan to implement a sequence modeling for the vision module and develop on-device speech recognition capabilities and enhance multi-person tracking. In summary, our prototype demonstrates a potential of combining vision and audio analysis for real-time falls and distress detection. The vision module shows high precision, while the audio module highlights areas for improvements in noisy environments. By fusing both modalities, we can enhance our overall system reliability. And thank you for your attention. And here is our GitHub page, which contains all of our work. This is still a conceptual code without implementing to devices, but in the future we are planning to do so.